Hello, I'm Michele Chiari and I'm a PhD student from Politecnico di Milano. This talk is about our work on the verification of floating point C and C++ programs which contains call to mathematical library functions. So why should we bother verifying this kind of programs? Well, because they are increasingly used in critical systems. And why is that? Well, it's because of the wide adoption of the IEEE 754 standard, which provides a reliable environment, which is okay also for safety critical systems. But what does it mean to verify floating point computations? Well, there are three main goals. And first of all, floating point computations react to errors by returning special values. For example, if we have an overflow, we get plus or minus infinity. And if we have a division by 0, we get not a number. If a function is called with a value outside of its domain, we get another number. These special values might seem apparently harmless, but actually they can create very nasty bugs if they are not checked. For example, if we try to convert an infinity or not a number to an integer, we get an undefined behavior, which is very bad. The numerical analysis literature already deals with most other goals, such as finding sources of round-off errors and also proving error bounds for the program. Here in this work, we focus on this kind of undefined and undesirable behaviors. So let's look at this example code. It's a function that implements the ghost error function, which is very much used in statistics. And this function is defined on the whole real number domain. And so someone that uses this code will expect an implied post condition that it never returns not a number, because it should be defined for all floating point numbers. So we must check whether this code actually abides to this implied post condition. And so we can, for example, start by checking which operations may return a not a number. So for example, the square root returns a not a number if it's called with a negative argument. So we can just use our knowledge from Calculus 101 and try to see if we can get a not a number here. So minus x squared is never positive, and consequently the exponential of minus x squared is always less or equal than 1, and 1 minus that is always non-negative. So we should never get a not a number here, right? Well, the answer is no. Well, actually, we found out that in some implementations, the exponential function returns a value that is slightly higher than 1 when called on a certain negative input. So we can get a not a number in this actual implementation. The problem is that this mathematical library function comes with very little guarantees on the errors of the computed results. So we don't really know very much about this error. So the approach we present here allows us to use these functions just as black boxes and do verifications anyway. So we just need to have access to the implementation. We use the framework of symbolic execution. So for example, if we take that line, we first convert it to static single assignment form. So we add a new variable for each operation and we assign only once to this variable the result of a single operation. So we end up with basically assignments that can be used as a constraint system. So we build a constraint system which is a verification condition for each possible execution path. And then we can add constraints to check for specific properties. For example, if we want to check whether we can have not a numbers, we can add z4 less than 0 and check if it's solvable. If it's solvable, then it means we have a counterexample and our assumed post condition is false. We use interval consistency to solve these constraint systems, which is a technique which comes from the constraint satisfaction problem domain. We first assign an interval domain to each variable. In this case, we add all the floating point numbers to them. And then we use projection algorithms or filters, which removes values that do not satisfy the constraint system. So if in the end we get empty domains, it means the constraint system is not satisfiable. Otherwise, it means we found a solution. So we can start here with z4 must be less than 0. So we remove from its domain all the positive numbers. Then we have z4 equal 1 minus z3. So we remove from the domain of z3 all numbers lower than 1 or equal to 1. And we go on by applying the propagation algorithms for all the constraints that we have. And finally, we end up with the solutions in the interval for z1. And all of the filters for these constraints are already present in the literature. We just need to provide the one for the exponential and mathematical library functions. So how can we make these projections? Well, since most of these functions are monotonic, the exponential is monotonic. For example, if we need to find a direct projection, so we infer the values for the output from those of the input, we can just compute the function on the bounds of the input domain. So we get the bounds for the output. But this works only on monotonic functions. But are these functions really monotonic? Well, actually, no. We found out by exhaustive testing of the most common implementation that very often they are not. So in this example here, we have a function which is overall increasing, so overall somehow monotonic, but there are some small drops in the function graph, and we call them glitches. So these drops invalidate this monotonicity because the function, instead of increasing, goes down a little bit. But luckily, we found out they are usually few, they are shallow and narrow. So we developed an algorithm that work with just this very general data about them. So for each function implementation, we need to know the total number of glitches, their maximal depth, and their maximal width, which are things that we can just find by exhaustive testing, at least for the single precision floats. Then, how can we fix the direct projection? For example, here we have a function with two glitches, and we need to compute the values for the range of the function, starting from the input. So if we just use the naive projection, which is the one we saw before, we get this interval, but actually, due to the glitches, the right one should be this one, which is larger. So we remove some values from the output domain, which are actually solutions to the constraint system. So since we have information about the maximum depth of glitches, we can just add and subtract that to the bounds that we just found. And so we found this bound, which are actually conservative, and they can be used for constraint solving. Things are a little bit more complicated for the inverse projection, which is the one that starts from the output values and tries to find the interval for the input values. So in this case, we use an adapted binary search algorithm, which is adapted to work also with glitches, even if there are glitches, provided we have reliable information about the data I told you about before. And these algorithms retain their logarithmic complexity, so they are still very fast. We implemented this approach in the Eclair software verification platform, and we compared it with the naive filters in the state of the art on a benchmark made of real-world code. We found out that our approach finds 26 anomalies more than the naive approach. And in particular, the naive approach deems 18 of them unfeasible, which means it says, okay, this bug can never occur, but actually it can, which is of course very bad if you want to do verification. So to conclude, with our approach, we made the verification of programs with calls to mathematical functions possible, which is something we, to the best of our knowledge, was not possible before. There are some caveats because we must have this data about glitches, and it can be gathered by exhaustive testing for at least single precision floating point numbers, and we can rely on that provided by the vendors of mathematical libraries in other cases. If this information is not correct, not so reliable, we can still find a fair amount of bugs. So it still works. We just cannot rule unwanted behavior out. Okay, so that's all, and thank you for your attention.
Hello, everyone. Welcome to this Q&A session. I hope you enjoyed the third paper presentation. I'm here with one of the authors, Michele, who is happy to take your questions. So please use the chat to ask questions. So far, I don't see questions in the chat. and so I will go first. So based on, let's say, on the title of the paper, the approach is supposed to deal with C and C++. And I wonder, how does it work with loops, aliases, pointers, all those features of C++ that might be present in the implementation? So what does it happen? How are they supported?
So thanks for the question. Of course, it's an important part of the implementation. Well, basically for loops, we do loop unrolling. So since the approach is based on symbolic execution, we unroll them for a given number of times. And well, for the moment, like this part of the prototype is not very advanced. So of course here there's a whole branch of research about deciding how to unroll loops, well, for how many iterations, and so on. And there is also a sort of very simple memory model in the tool, but we don't support many of the library functions you have in C++. So, for example, we still have a bit limited support for example, vectors, because in that case there's an external library call, and but so the main focus of this work is actually the mathematical libraries, and so that will be part. Of course, there's a plan on implementing this in a commercially available tool, and at that point they will address all these things, of course.
Okay, thank you. I see there is a question in the chat by Marieke. So nice work. If I understand correctly, you can verify implementation of floating point library functions. Could your work also be useful in some way to verify clients of those libraries, for example, for deductive verifiers?
Okay, thanks for your questions, Marieke. Well, actually, the main purpose of this approach is actually to verify the clients. So the algorithms that we used, that we implemented, are actually so they are based on a very simple analysis of the libraries seen as black boxes, and we use them for a constraint solver, which is used to solve constraints that come from the clients. So we model the clients with symbolic execution, and since they're in the clients, there are calls to the library functions. We model them as constraints, and then we use these propagation algorithms to solve these constraints. So actually, we do verify client code. And so the approach came basically for the purpose of verifying client code, and in a more practical way, because if you look at the literature, there's a lot of literature that is about bounding maybe the errors of these functions and things like that, but they all mostly need to do white box approaches, so to have the source code of the implementation and to maybe change the implementation so that it's maybe correctly rounded or more precise. Instead, we wanted to be able to do verification with any kind of library without putting constraints, well, with just minimal constraints on them. So what we want to do is to be able to verify code so that people can just choose their favorite mathematical library, because sometimes there are many other constraints for the choice of the mathematical library. So
Okay, we have a follow-up question, but then if the floating point computation is used in a larger context, how will you verify the larger context?
Well, of course, that is still a problem that we don't address completely. So what we are able to do is a symbolic execution on these programs that use these libraries. For now, the length of these programs is not very large. So if you look in the paper, we did an experimental evaluation, and the programs we used are up to hundreds of lines of code. So it's feasible on computational kernels. Of course, if you have a much larger application, it becomes harder, but it's also a limitation of symbolic execution, because so you get this formula, maybe one for each execution path, and then you have to solve it. Of course, you need to have a solver that is able to. So you're limited by the solver. So if by the larger context you mean the whole application, we still have work to do on that, of course.
Okay, thank you. Okay, I don't see other questions, so I have another question. If your analysis has to be aware about the glitches, and in the presentation, I think you mentioned the usage of exhaustive testing as a way to discover the glitches.
Yes.
I wonder, well, one point is that exhaustive testing could reveal the problem itself. So I wonder how often, like, exhaustive testing is able to reveal the glitches as needed by the verification, but not revealing the problems that can be later revealed with the verification step. So I wonder.
Well, of course. Well, first of all, the exhaustive testing of a mathematical library is different from the exhaustive testing of a program. So the reason why for a mathematical library it is feasible is that we have just one input variable. So if you have a 32-bit floating point number, on modern computers, you can do that in minutes. And also you need to do that, so the exhaustive testing, just once for each library implementation. Okay. So once you have chosen your implementation, you do the testing, you gather this information about glitches, which is just a few numbers for each function, and then you can verify just with that information any program that uses those libraries. Okay. So you do that, the heavy work once, and then you apply it on many different programs.
Okay, I see the point. The verification is for the larger context, and so the testing is to extract.
So the verification is okay. for the client code. The exhaustive testing is for the library. And yeah, maybe that was not clear enough in the presentation, because if you both have had a doubt on this, probably I should have clarified that better.
Out of time, but we have maybe a quick follow-up question. I was thinking that maybe you could generate some specification which then could be used by another tool. I think that would be an interesting way to combine tools. A quick comment on that.
Well, it depends on what you mean by specifications.
I think you have 20 seconds left.
Okay.
I think you can take this question in the breakout room.
We can
maybe,
go on in
you can exploit the breakout room, because we are running out of time. So let me exploit this. Take these 10 seconds to thank Michele, thank the audience for attending and for the questions. And I think this is the end of this Q&A session. Thank you.